Hello, everyone, and welcome to this week's of asynchronous content. We're at week 4 in terms of asynchronous content and week 5 material in terms of the in-person. So when we meet next Thursday, we'll be discussing the material from these lectures and a few other selections of topics from biofluid mechanics. Welcome again to the module, and I hope that you've had a brilliant couple of weeks so far. I'm Dr. Hussein Haydari, and I will be your instructor for the remaining weeks of the module. Dr. Karen Hing has already gotten you familiar with some of the key topics in terms of materials in dentistry, the structure of the biological systems in our teeth and bone tissue. And now we're going to move on to a different set of organs in our bodies. So we're looking at the cardiovascular systems and the subsystems involved here. This week and next week as well, we're going to continue our lectures. We're going to look at the material aspects and discover some of the devices that are used in cardiovascular diseases. So without further ado, you can see a couple of images here. I've tried to put in a variety of things that we'll be covering. We'll be looking at the anatomy and physiology, as well as the function of the cardiovascular system, our heart and our vasculature. We'll be looking at some efforts in 3D printing and producing these interfaces, models of our cardiovascular system, as well as functional devices that can be implanted there. So we'll be looking at a bunch of devices as well. But to start this week, we're going to first look at the function of this system. We're going to look at the various subsystems involved. We're going to look at the history of cardiovascular models. Then we're going to take a look at the importance of it and various cardiovascular diseases. Looking at these diseases, you'll then figure out what sorts of solutions and material and device combinations have been used to date, and we'll try and look at the most recent advances that have happened in these past couple of years. So to start, we're going to take a look back at our itinerary for this semester. We've already gone through the first phase to a good extent, which is the starting point. It's dentistry and materials in dentistry. Now we're moving towards the cardiovascular system, a little bit more sophisticated because we're dealing with both material properties that are trickier to work with and also systems that are a lot more complex than our teeth and bone. And then we'll continue moving on to our lung, skin, and other systems involved in the excretory system. And then we'll be talking about manufacturing of human tissues and organs. So just a recap of where we are right now. If you remember again from the first lecture that we had together, and looking forward to see you all again, we had this Mentimeter that you filled in with all the devices that you knew about. And as you can see in the center of it, you've got pacemaker, stent, catheter. So these are pretty much devices that you've all heard of. And they're some of the most common devices, these cardiovascular biomedical devices. And today and during this week and the next, we'll be looking at them more systematically. So you'll be learning about various types of disease, and you'll be learning about solutions that we found to cure these diseases and treat them. So we're going to talk a lot about these devices, especially next week. So the structure is going to be following this bullet point slide here. We're going to start with the importance and significance of cardiovascular science. We're going to talk about some historical perspectives and give you an idea of what the models were in the past. We're going to look at the human circulation circuitry, the network that connects the heart to the lungs to the entire body through vasculature. And then we're going to look at an engineering aspect of this system, which is the fluidics. We're going to look at biofluid mechanics because it's very important and key towards our device design and material selection later on. Then we're going to move on and talk about cardiovascular disease and medical devices, implants, and materials that are used for these applications as we move on to the next week. Okay, so to start, let's first look at cardiovascular disease. So cardiovascular science is very important, and the reason for that can be easily understood and realized from this plot here. So it's interesting to know that for a long while in the history of humanity, diseases such as viral infections and bacterial infections were the main cause of human death until we were able to tackle the majority of those. And towards the beginning of the 20th century, with more engineered solutions for those primary types of human disease and causes of death, it started to show that human heart diseases, cardiovascular diseases, cancers, and other more complex types of human disease started to become the major cause of death. So especially towards the 1920s, we saw that the cardiovascular diseases increasingly became the common cause of death. And this peaked all the way until the 1960s. And as you'll see, the history of medical innovations shows that this was around the time that we had understood the cardiovascular system very well, and we had started to innovate on medical devices and the treatments, prevention, and diagnosis. Were so advanced that this started to decline. And so fortunately, this is a very good example of us being able to innovate and engineer devices and systems to cure a significant portion and contribution to the overall death rates. So now you can see that cancer, for instance, is now becoming the leading cause. So the longevity is basically exceeding heart disease and heart failure. We're able to tackle that and repair those conditions, but now cancer is taking a great slope of increase as the major cause of death. So this is very good news, but still CVD, cardiovascular disease, remain the leading cause of mortality as we speak. And there is still lots of room for innovation in this area, as we'll see later on. If we look at the demographics, it's actually not true that cardiovascular diseases are, mainly a problem in our country, in the US and in other industrialized countries. It's actually a matter of fact that it has a good proportionality basically with the wealth of these countries, with the availability of these treatments, especially nowadays, where lots of these conditions have already found solution. We now have an issue of getting those to these different regions in the developing countries and underdeveloped countries. So this is a big issue to reduce the cost of these medical devices that are rather still, even as we talk, are still rather complex and sophisticated in their design and manufacturing. And so, this big figure, 1/3 of all causes of death worldwide is from cardiovascular disease. So another thing that's wrong is the belief that it actually influences older men. more than women. As you can see, it influences both populations, actually more so often for women. And again, it is the leading cause of death for both women and men globally. And the risk factors, we'll get into this in a lot more detail, but are known to be smoking, tobacco, cholesterol levels, hypertension. A lot of it can also be genetic, and inactivity, which is sort of the leading cause in today's world in a lot of the countries that are dealing with cardiovascular disease. So moving away from this, so you actually see how important it is. Now we're going to look at the history of cardiovascular science, and this is where I'm especially interested in and excited about, because I always love to talk a little bit about the history and the trajectory that an area of science has taken until it actually became of this level of advancement that we are familiar with today. So to talk about that, we're going to start with Aristotle, and he was actually the person who sort of started some systemic reviews of the structure of the heart and cardiovascular system. But it was very interesting that he actually believed that the heart was a source of heat that would endow blood with its internal heat, and that the blood was the general nutrient fluid that would, basically perfuse the entire body, and it was just held in our hollow vessels, such as water in a vase. So there was no idea of flow here. It was just a filling liquid that would fill our bodies, just like right now we know the water in our bodies has a similar behavior. It was believed that blood was the same back then. And there wasn't a clear distinction between arteries and veins, of course, and the pulsing behavior of the heart that they could observe back then was considered to be these fire, sparks that were then, generating lots of heat and then cooled by the air that was taken in by the lungs. And the lungs were basically also full of these vessels that would take in the pneuma when you breathe, to bringing the air and actually oxygenate. Well, back then they didn't have an idea of oxygenation, but in general that was the idea. Very basic understanding, but still based on the observations that they had back then, until Praxagoras actually improved it a little bit. He understood that the arteries and veins have a distinction. Arteries pulse, but veins do not. And he believed that arteries contain the air, whereas veins contain the blood. And that's interesting that this naming has actually remained the same until now. So we have arteries, meaning the channels that are full of air, still here up to the present day. And he thought that the arteries stemmed from the heart, but the veins came from the liver, which is interesting, filling the body with blood, and the arteries filling the body with air. And they both had beliefs of, the heart being second to brain in controlling movement and our sensations and our thinking and lots of that. But it was all refuted later on, obviously. The third person I want to mention is Galen, and he actually was a very important figure in ancient medicine, a master of animal dissection, and he was able to restore function of arteries, so did surgical procedures, but then he did not appreciate the circulation still, and he believed that these veins and arteries all carried blood. He didn't believe that arteries just carried air and veins carried blood. He believed that both would carry blood to the extremities of the body. And his idea was that the septum, which is the layer separating the left and right part of the heart, as we'll get to, was perforated so that the air, pneuma, would be able to get distributed. And I'll show some figures to show what he meant from the left to the right heart sections. And he also thought a similar idea that the heart was a furnace that would boil the blood and heat it up. And that was because he also saw the change of color from purple to red as the blood got oxygenated as we know it now. But again, they didn't know what oxygenation was all about. But he realized that the change of color in blood, and he thought that it was boiling and temperature changes. Columbus actually was the next figure who did actually start thinking about circulation and realized that the septum isn't perforated, and still thought that the lungs were the air supply. And this was pretty new, not the heart, and that this was an interesting observation that he realized the pulmonary arteries, meaning the arteries that go from the heart to the lungs, are too large. They cannot just be there to serve the lung like every other organ. They're actually carrying a lot more blood than would be necessary for the lungs. So he had these bits and pieces of information telling him that a larger flux of blood was going from the heart to the lung, meaning that this actually was a sign of, lung having a more substantial role. And then Cesalpino started the idea of circulation. He termed it circulation and recognized this back and forth between the heart and the lungs. But he didn't talk about systemic circulation to the body, mainly between the heart and the lungs. And he realized that the veins were there to return the blood back to the heart. And this is really when we started to see experimentation, very well detailed experimentation in terms of cardiovascular science. A figure that you've probably heard of, William Harvey. We have the William Harvey Research Institute at Queen Mary, named after him, a major figure in cardiovascular research. And he was the first to really think about circulation the way we know it now, meaning that blood would carry on through our arteries all the way through the organs and then collected by the veins back to the heart. The full loop of circulation associated with blood. He was the first to really recognize that. And he did that using very simple experiments, but very clever for that time. He would, for instance, block a vein here in the arm, first of all, making sure that these veins would pop out by exerting pressure there on the blood there to pressurize it, and having the person hold something firmly so those blood vessels will appear a lot more bold. And then he would actually block the vein with his finger, showing that the rest of the vein back to the heart would empty, meaning that there's a directionality to the blood flow in the vein side that is not the same in the artery side. So basically, he showed that there is flow back towards the heart through the veins. Another experiment he did was he would fill the left atrium and ventricle in the heart with water in animals, of course, and then have it circulate through to the right ventricle and atrium, showing that actually until the main fluid stream, the aorta was blocked, nothing would carry on, so it's not perforated. But then once you open the aorta, it all flows in. So these were all, I mean, when I show you the diagrams, will make a lot more sense, but these were all signs of circulation in the entire cardiovascular system that he was able to detect by blocking one point of the network. After William Harvey, there were lots of other improvements. Here are some names mainly involved in understanding the fluidics, which is a major part. The engineering of the cardiovascular system relies strongly on our knowledge and understanding of the fluidics, as we'll get to it in our in-person lecture next week, and a little bit of it in the next asynchronous lectures of this series this week. But what they realized was, generally the flow of a liquid in a channel, and the equations governing that motion, which was then applied to biofluids in the body, and the understanding of the resistance of a channel, which was then translated to the resistance of blood vessels and all other vessels in our body. It was the initiation of fluid mechanics approaches to understanding the biomechanics of our body, which was very novel at that time and still now. And so these were a couple of those main names: Bernoulli, Euler, Thomas Young, and Inge Purcell, Navier-Stokes, as well as Stephen Hales, which was the person who first measured blood pressure with these intravascular pressure probes. And the idea of just looking at it a lot more engineered approach than before. So this will hopefully make it more clear what these models were in comparison with each other. I'm going to ignore the model back there from Aristotle and look at the more advanced one starting from Erasistratus. So this one, actually, the first one you see here, I can't even pronounce, Erasistratus, but basically based on the Pythagoras model. The idea here was that air would go through the heart from the left side of the heart, the left ventricles, and the blood would be circulated through the right. And these were two different streams, air and blood, and they would be supplied to various parts of the body in separate networks. The second idea was the perforation, which Galen had, and he thought that there was a blood with low air, low oxygen, and a blood with high air, high oxygen, and these two were connected with these porous perforations in the membrane or the septum, and that would allow the exchange of low oxygen and high oxygen blood, or low air and high air blood back then. And then the idea of Colombo's circulation, which was a preliminary idea that there was a circulation system in the pulmonary side going from the heart to the lung, but the other side going to the other organs, including the brain and everything else, was all just one way. So it would go and not return, which was pretty interesting. So this was the first time that William Harvey demonstrated that no, it all loops back. It cannot just go there and disappear. Such a large mass, it can't just go all the way to the extremities and then diffuse. It has to come back and circulate through the heart and the lungs. So with this figure, I'm going to leave you there until we meet next time for the next bit of the asynchronous content, where we're going to talk about the anatomy and physiology of the heart. Thank you very much, and I hope you've enjoyed this first part of cardiovascular system engineering. Thank you.